easy for you to do now to just do a brainstorm of what you remember from enthalpy. All right. So first off, definition-wise, what we are talking about with enthalpy is what? What is enthalpy? Something about disorder? You're thinking about entropy. It's okay, though. We're going to learn about entropy. I am sorry. I don't know what's going on with it. All right. Enthalpy is referring to the heat change in a chemical reaction. Catherine, can you close that window? Because it's, like, making me nervous. All right. There are two types of things that can happen. The first thing... Oh, can you get it? You might need someone taller. Or you can get on a chair or something. There you go. All right. So, with this heat change, gentlemen, are we listening? A lot of you guys want to do thermo instead of organic now, so you got to hear. All right. So, one thing that I have to keep in mind with enthalpy is that the energy can be released to the environment. When we touch something that is releasing heat energy, it's going to feel hot when we touch it. And so that is endothermic or exothermic? Exothermic. So if you touch it, it will feel hot. If we are thinking about this as a graph, let's say I had a graph and I was like, the time of the chemical reaction, I have my reactants and I have my products. They will have different energy levels. Will the reactants have more energy or less energy than the products? More, because it's losing it. So in the initial reaction, my reactants will have quite a high amount of energy as the reaction occurs, and then we make our products. We see that the energy that's stored in the bonds are being lost. So this section here is referring to the energy loss. That's going to be released into the environment and thus feel hot. Does that make sense? It's kind of counterintuitive. All right. Something else to kind of keep in mind when we're thinking about these reactions is that bond breaking releases energy and bond breaking absorbs energy and bond making releases energy. I'll add that as a side note. Bond breaking requires energy. And should capitalize these letters. Making releases energy. Okay? The way I like to think about it is two magnets. When I put two magnets nearby each other, they automatically want to snap together, making a sound. Whereas if I have these two magnets and I'm trying to pull them apart, I have to use force in order to do that, and that's breaking the magnetic attraction between them. That's the way I like to use it as my analogy. So I think about those two magnets. If I want to force them apart, it's going to require energy for me to do that. Once they break apart, or once they join back together, they join together really easily. And then, like I said, that's going to be releasing energy. Remember, with these bonds that are being made, it's being made because it's increasing the stability. So that's why it's releasing all that energy. More stable that way. Are we okay with that? Okay. Next example that we are thinking is the endothermic. Actually, let me help you guys remember your terminology. Exothermic, I think excited. You are excited and you're releasing all that excitement, thus releasing all the energy. Endothermic, I think end, like when you die, you are cold. It's a very dark way to think about it, but it works for me. So energy in this case is being absorbed from the environment. So again, if I have a diagram and I'm trying to show that happen in a chemical reaction, I have my reactants, and then the reaction occurs, and now I have my products. So there's my reactants, there's my products. And this here is representing the energy that was absorbed from the system. The other thing to keep in mind is the delta H. So if the delta H is endothermic, will it be positive or negative? Do you guys remember? Positive number. If the delta H is exothermic, it will be a negative number. So that's a quick way to check what you are dealing with. All right, I'll give you guys a second to get that down. Questions, concerns, or comments? It's what we covered last year. Huh? Yeah, delta. Yeah. Oh, you're triangle. It just means triangle is referring to change. So I'm talking about change in heat. The change in heat is negative, then it's exothermic. The change in heat, it's positive, it's endothermic. All right, we good? All right, I'm gonna move it on to the next page if you guys are okay. I'm gonna keep on the same page. No, I'll start on the next page. It's a new set of ideas. Okay, so some things we are now going to be thinking about then is different types of chemical reactions and what that's referring to. So, first thing we're going to be talking about is latent heat. That is referring to phase changes and things like that. So, when I am looking at a reaction, let's say time, and as time is occurring, I'm heating a substance. Let's say I'm starting with something like ice. So ice is a solid at 0 degrees. And let's say I start heating that ice so that way it starts melting. So let's say actually I'm at below 20. So I'm at negative 20 degrees Celsius. I'm starting to heat up an ice cube until it's at 0 degrees Celsius, and then it starts to melt. All right. Then I have water, and when I have water, again, it's increasing in temperature. Say, for example, you have like room temperature water, you have ice cold water, you have room temperature water, you have boiling water. So again, the temperature is going to increase, and then at 100 degrees, it's going to start doing another phase change. And then after that, you have steam. So we're dealing with water in this case. This is temperature in degrees Celsius. All right. So my first question to check understanding, if I'm heating this ice cube until it's a gas, is this an endothermic or exothermic reaction? Endothermic. So don't get confused when you're like, oh, but the water's getting hotter and I'm boiling the water and that must be exothermic because the water feels hot. Think about the process in which you are doing to heat that water. I'm putting it on the stove, and in order for that water to start boiling, I need to give it some heat energy, and that's getting absorbed by the water to allow for that temperature change and then the phase change. So be mindful about those sort of things. If I am boiling something, or if I am vaporizing something, that's another way to think of it word-wise, or if I'm melting something, those are all examples of endothermic reactions because I need to absorb heat energy to do those changes. Do you want me to write that down? Are you guys okay? Okay. If I want to do the reverse, and let's say I want to go from gas to liquid or liquid to solid, so I'm condensing or I'm freezing, again, it is going to now be an exothermic reaction because I'm trying to remove heat from my water molecules to get it to slow down and then change state. So that's why I take let's say I had a tray and I put it in the freezer with water. I'm going to put it in the freezer because the freezer is cold, and that's going to be a means to then absorb the heat energy coming off of the water to allow that phase change. All right, so that's what we're thinking about. Something to keep in mind is at this point here, when I have my molecules and I'm heating them up, the reason why the temperature is increasing is because my molecules are starting to move faster. So temperature is a representation of what my molecules are doing speed-wise. So my molecules are moving faster and faster and faster. The temperature is going to increase and increase and increase, and then I suddenly hit a plateau. This here is known as latent heat, and this is now what we're talking about when it comes to temperature. So we notice the temperature steadies, and we notice at this point it is melting. So what is happening at this point is that instead of the energy going into my molecules moving faster and changing temperature, the energy is now being used to break bonds or break forces to allow the state change. So that's why the temperature is remaining the same for a little while. Once I have broken all the bonds, or most of the bonds, enough to make it go from a solid to a liquid, it's now going to be able to start heating again because now my molecules can use, now that heat that's being provided to the molecules can get them to move faster. So that's going to cause increased temperature until I hit this point again. And then once again, I need to put my energy into breaking bonds or forces instead of having the molecules move faster. So that's why you see those points of leveling. Okay? Are we okay with that? Okay, so now let's go into some of the information that is going to be talked about this year so you guys know how to read little bits of information. What they're going to do is they're going to give you little delta symbols with little bits of information. I'm trying to think. Fusion. I might need to look at a book. All right, so you have delta. Let me just go find a book real quick because I need to remember what symbols I need. Only so much my brain can hold at once. Chapter 10, 7. Okay. Just trying to find my letter. Combustion, formation, or the phase change ones. Is that fusion? Let's see what they are. When did it happen? Might just have to Google it because my brain's not working. Oh, there it is. I can see it now. Oh, yeah, I was right. Fusion vaporization. Okay. Delta F H, and then you also have delta vape H, like that. Okay. So, just want you guys to be mindful of these terminologies, just in case they come up. Yes, they're melting and boiling point. Yes. Okay. Cool. So, so you guys will often see delta H, but there's usually these little subscripts in front that kind of give you a hint of what type of reaction's occurring. If I see the FUS, that says fusion. So this is talking about the energy required to melt. So this one here is melting. And if I see VAP, that is vaporization. So we're talking in this case about boiling or evaporating. So if I was to, let's say they have the water molecule and they're saying, can you draw the equation to show the fusion of water? So if I wanted to show the delta fusion of water, it would be H2O, the salt, S, going to H2O, the liquid. So just want you guys to be aware of what that looks like. If we have vaporization, because they often ask this question, now we're going to the gas. So the thing to remember when we're looking at these guys here is that we are still dealing with the same molecules, we're just dealing with a phase change. Are we okay with that? All right, 2 more? Actually, kind of 3 more. Okay. Another one for you guys to learn is there's delta FH, and that is fusion, or sorry, formation. There we go. Now the rules for formation is we are looking at making 1 mole of the substance from the elements. So for example, if I was trying to make, I'm trying to think of one. let's say I was trying to make butane, which is a gas. I would need to backtrack and make it from the corresponding elements. So carbon and hydrogen. So C S plus 2H2 gas. So that is an example of a formation equation. When we are when we are writing our formation equations, it is important that the product, what we're trying to produce, is set to 1 mole. So if I'm looking at the formation enthalpy equation, and what does that mean definition-wise? It is making 1 mole of substance from its corresponding elements at standard conditions. And when I say standard conditions, I'm talking about 25 degrees Celsius, 1 atmosphere pressure. Okay? It is okay for us to have fractions in these equations. I'm just trying to think of one off the top of my head. Let's say, for example, we're trying to make ammonia, like that. All right, I need to backtrack and make it from its elements. So if I had ammonia, it would be nitrogen and hydrogen. Okay? Now, this is the one and only time you are allowed to use fractions. This is a 1, this is a 2. So I only need half a nitrogen for that. This is a 2, that is a 3. So I need 1.5, or you can write 3 over 2. This is the first and only time in your life that that's going to be acceptable. I know we've talked about balancing equations when you guys were in earlier years, but now we're actually doing something weird that you haven't seen before. Are we okay with that? Fractions. All right, there's one more I need to show you guys, and then we can start talking about Hess's law. Just seeing how long the notes are going. We probably can take a little break. All right, move it.
Is it like into like plus H2? Into plus H2.
Yeah, that's what you're supposed to do.
And
So the reason why it's a half is because I only need 1. So if I do half times 2, it's 1. 1's on that side. I'm just doing counting atoms. In this case here, I have 2. In this case here, I have 3. So I only want 1.5 of the hydrogens, because that if I do 1.5 times 2, then that's 3. Fractions. They're coming back to bite you. All right. The other thing we see is delta CH. That is combustion. Oi. Do you want to do thermochemistry? Then zip it. So this is combustion. With combustion, it is based off, again, having 1 mole of your item that you're burning. So let's say, for example, we have ethanol, CH3CH2OH. Let's say I have that. Or if I want to write it in the condensed formula, C2H6O. All right. With combustion, we are burning it in oxygen. So we're going to need oxygen, O2. Something to keep in mind is that when we are doing these equations, this one here is set to 1 mole. So everything is in reference to the thing that's getting burnt. When I think about the product, when I'm burning it, I'm making a combination of carbon and the hydrogen. So carbon with oxygen is CO2. Hydrogen with oxygen is H2O. And then once again, we have to play the balancing game. So first thing I need to balance is going to be my carbon. That's 1, 2. That's only 1, so a 2 is going in front here. The next thing I would balance for is the hydrogen, because that's the easier one too. So that one is 6. That's 2. So if I divide that by 2, that's 3. All right. The last thing I'm going to do is balance for the for the oxygens. Let's do a count here. So 2 times 2 is 4. 3 times 1 is 3, so I need 7. This is 1, so I need 6 more from here. So that's why a 3 is going here. Balancing equations. Welcome back. Are we okay? I'll give you guys probably about a 5-minute break because I noticed I'm talking for like 20 minutes. And the next thing I want to show you guys is an exam question. So yeah, give you a little break. Do you want me to have it as one big video? Or do you want it 2 separate videos? 2 separate? Okay.